あれあれ It's 11 in Japan time, so maybe お願いします。
So, can we start?
Yes, please.
Okay. Hello. My name is Junpei Shirai from Japan. It's my pleasure to be here to chair the session. So let's get started the session. So there are three presentations in this session. One is supernovae, and other one is a reactor neutrino experiments. And last one is a review on underground laboratories. So the first speaker is Kotake-san from Fukuoka University. His title is Supernovae, Neutrinos, and Gravitational Waves. So please start, Kotake-san.
Thanks. Can you hear me? And can you
Yes.
show and see my slide? So I would like to thank the organizers for having me to this prestigious conference and also making this TAUP effort happening under these social circumstances. So today I'm going to give a review talk on core collapse supernova modeling with neutrinos and gravitational wave signals. So what I'm going to tell you is based on a number of ongoing projects with my colleagues. The list of short list is shown here. And my particular thanks goes to Takami Kuroda, Tomoya Takiwaki, Ko Nakamura, Shota Shibagaki, who did nice 3D simulations that I'm going to show you in my talk. All right. This is a short recap slide. So the best studied mechanism to blow up massive stars, say 9 solar mass, is a neutrino healing mechanism, which was pioneeringly proposed by Colgate and White in the middle of the 1960s. So maybe you have ever seen this animation before, but sorry about that, but I would like to show you again for a broad audience. So this is an example of explosion of an 11.2 solar mass star, which we did with Takiwaki-san, Swasan, and myself in 2012, almost 10 years ago, using the fastest supercomputer K at that time. So let's jump into the iron core. At the final fate of massive stars, the iron core, the central core, is gravitationally unstable and it begins to collapse. And when the central density exceeds nuclear density, you can see the shock formation, but the shock stores in the iron core. You can see a firstly round shock, but inside the round shock, you can see a number of hot bubbles. This is because of the neutrino heating. The neutrino is leaking out from the protoneutron star, and you can see hot bubbles seen in this animation in red. And you can see that these hot bubbles is gravitationally unbound because they get enough high energy from neutrinos, and you can see a dynamic explosion. But this is a supernova explosion that was obtained in supernova in super computers. And if the supernova is taking place in our galaxy, we can see a number of neutrinos, not two like this, like 10,000 of neutrinos, and you can see the shaking of gravitational wave detector. This is actually a exaggeration, but what I would like to point out is that we should not miss the next galactic event, because the event rate of of the supernova in our galaxy is about 100 years. So this is a once in a lifetime event. So the thing here is how we can observe neutrino and gravitational wave signals, and also the thing is what we can learn about the supernova physics. But to make this happening, we need to have a lot of sweat. I wrote sweat, sweat, sweat. What does it mean? So maybe I would say to develop big simulation code, like including supernova code, maybe equivalent to develop big experimental facilities, because they need a lot of manpower. So what is the final goal for the supernova simulation? We have to deal with distribution function of neutrinos. So F, neutrino distribution function, depends not only time, 3D in space, and 3D in momentum space. So we have to deal with 7-dimensional neutrino transport problem in general relativistic space-time, also with magnetohydrodynamics. This is a tremendous work. So we need 3D GR simulation with 3D neutrino transport direction. And this is star marks the final goal. This is a headline of the code development. Our colleagues in Japan, Sumiyoshi-san, Yamada-san, Nagakura-san, can deal with 7-dimensional neutrino transport, but unfortunately at present with Newtonian gravity. And my colleagues in Germany, like Thomas Janka and Bernhard Müller, now in Monash University, can deal with 2D general relativistic simulation with very sophisticated neutrino transport, but limited to axisymmetric assumption. And we can do 3D general relativistic simulation, but with M1 transport, meaning that this is also approximate neutrino transport. This is a headline of the code development. And also, I would like to emphasize the Valencia supernova group led by Miguel Angel Aloy and Martin Obergaulinger is now doing a special relativistic MHD simulation in 3D. This is also world leading. And then you can see that over the 4 decades of code development, we are very close to the final goal. Don't you think so? Anyway, so this is a cube type plot. So this is rather difficult to see, and so I plotted in 2D space. So what we need is 3D simulation in space and full general relativity and reaction rate, neutrino reaction rate with improved nuclear equation state and full neutrino transport. So from my team, what we can show here first is a simulation with this circle, orange circle, 3D simulation with approximate general relativity and full neutrino reaction rate and approximate neutrino transport. And this is an example how neutrino opacity impact the explodability of the star, meaning failure of success of explosion. Now you can see that for the 20 solar mass progenitor, let's forget about the detail, but using the standard neutrino reaction set proposed by Stefan Bruen, 1985, no explosion. So updating the electron capture rate to heavy nuclei by Karl-Heinz van Ganke and Martinez Pirino, no explosion. Updating these reactions, no explosion, no explosion. And updating the, including the biliary correction to the neutrino nucleon scattering rate, we can see the late explosion. So this is a sort of demonstration, but I would like to show you that for the quantitative gravitational wave and neutrino signal prediction, we do need the update in neutrino opacity. We do need the accurate neutrino opacity. Otherwise, we are simply mistaken because explosion or non-explosion is very sensitively dependent on the neutrino reaction rate we employed. So using the best available neutrino reaction rate, we are now doing 3D simulation. And this is an example of 20 solar mass progenitor. And you will see that this box size is changing with time. This means that the shock wave is now getting bigger. So behind the shock, you can see the formation of red region. This is a high entropy bubble region. This is a simulation done by Takiwaki-san. And you can see that the shock wave is now going out of the 1,000 to 2,000 kilometers. You can see the explosion, successful explosion for this model. So this is the shock trajectory of the 3D model comparing to the 2D model. As you see, 2D explosion is too optimistic compared to the 3D. 3D is more correct answer. On the other hand, in 1D, we don't get explosion. So just it's important to note that 3D shock trajectory obtained in your simulation is consistent with previous simulation done by Garhin team, Melson et al. And Thomas Yanka et al. 2017. And for this 20 solar mass progenitor, the explosion was triggered by convection. So this is for the explosion of 20 solar mass. So what about other progenitors? So we are now doing many more 3D modeling with magnetohydrodynamics. This is worldly first. This is done by Nakamura-san and Matsumoto-san. You can see the explosion of 9, 10, 11, 12, 15, 20 solar mass progenitors, all of them are exploding for the yes, for between among before 500 millisecond post-burst. So this is a comparison of shock radius as a past. This is the evolution of shock radius as a function of time after bounce. So using the similar progenitor set, this is a result from Princeton group led by Adam Burrows. Please note that their 3D simulation is not MHD. So our simulation is 3D MHD. So that there is a qualitative agreement between their result and our result. That almost of the 3D models are trending towards explosion, but our models are more easy to explode because we consider the MHD. So magnetic pressures pushes the material behind the shock. This is the reason why our 3D models leads to more easier explosion. And this is the neutrino detection rate at Super Kamiokande in the left panel, and the neutrino detection rate at Hyper Kamiokande for galactic source. You can see a number of lines. So you can see from the y-axis, we would never miss these 3D explosion supernova in our galaxy by not even by Super Kamiokande, of course not by Hyper Kamiokande. And you can see that the high detection rate and the low detection rate, this is because of the compactness of the progenitor star. If the progenitor star is gravitationally compact, the neutrino emission rate is high. On the other hand, if the progenitor is gravitationally loosely bound, meaning that this is less compact, the neutrino detection rate becomes small. So this is what we found, and this is consistent with also with other studies. And I'm moving on to talk about gravitational wave signals from our 3D models. So I just chose to show two models: 9 solar mass progenitor in red, 20 solar mass progenitor in purple. The 9 solar mass progenitor is the most less compact star. The 20 solar mass progenitor is most compact star. So as you see, that gravitational wave signals is stronger compared to the gravitational wave signals compared to the less compact star. This is not surprising, but you can see that these signals are detection limits of the advanced LIGO, advanced Virgo, and Kagra detectors for the galactic center. And it's also important to mention that the proto-neutron star astroseismology is very important technique to extract the information of vibration of proto-neutron star. And the Valencia supernova group has done a very nice pioneering work. And that is a paper by Alejandro Torres Forne, Pablo Cerda Duran, Tony Fonto, which appeared in Physical Review Letter 2019. They developed the so-called great code. So by using the great code, we did the proto-neutron star astroseismology analysis from our 3D model. So this is a waveform, gravitational waveform, and you can see the gravitational wave spectrogram in the bottom panel. So forget about the detail, but this white line is a fundamental F mode, is well overlapped with the excess of the gravitational wave spectrogram. Red region is a excess of the gravitational wave is well overlapped with the fundamental mode. And looking at very carefully, you can also see the avoid crossing between the F mode and the G mode of the proto-neutron star vibration. And so what we can learn from this right panel is that F fundamental mode, fundamental oscillation mode of the proto-neutron star can be observed by the LIGO and the Virgo and the Kagra detectors. And by looking more into detail of the oscillation of the proto-neutron star, we can see how the detail of the oscillation of the proto-neutron star. Oh, I forgot to mention about the knock the watermelon. Maybe I don't have enough time, but if you want to buy a good tasty watermelon in Japan, we are told to knock the watermelon. If the sound of watermelon is, if we knock the watermelon, if the sound is like don don don, low frequency sound, it means that watermelon is very sweet because it has a lot of water or it's dense. On the other hand, if we knock the watermelon, if the frequency is high, ton ton ton, this means that the watermelon is not so juicy. So this means that watermelon may not be so delicious. So anyway, by knocking the proto-neutron star, we can see the vibration mode of the proto-neutron star. This is the F and the P and the G mode. So the detecting the various, oscillation mode of proto-neutron star would be the next step to understand that, of course, nucleation of state and physics of general relativity in the next round. Okay. And as I mentioned, we are doing 3D magnetohydrodynamic simulation. We can also compute the field geometry of magnetic field strength. So firstly, this is magnetic field strength was assumed to dipole shape, but after bounce, you can see that behind the shock due to the convective motion, the magnetic field configuration is totally chaotic due to the chaotic motion in the post-shock layer, but later in post-bounce, the material outside of the proto-neutron star is almost expelled from the center. In the end, so we can observe the dipole magnetic fields in the vicinity of proto-neutron star. When we make a crude estimate in the vicinity of proto-neutron star, spin rate of proto-neutron star is 200 milliseconds. The proto-neutron star gravitational mass is 1.5 solar mass. This is consistent with expected value observations. So this is a so-called one of the success of, I would say, the neutrino-driven explosion mechanism of massive stars. Okay, now I'm switching gears to speak about the other types of explosion. This is a result of 27 solar mass progenitors. So you can see after about 150 milliseconds, 200 milliseconds post-bounce, you can see the shock oscillation, the dancing of the shock instead of the neutron-driven convection. This is a so-called standing accretion shock instability, or simply SASI, which was named by John Blondin. In this case, reflecting the shock oscillation, we can also see the modulation of neutron signal due to the shock dancing of the shock. the modulation frequency is, of course, determined by the shock oscillation. And by taking the Fourier spectrum, time spectrum, we can see that peak frequency of neutrino signal is about 80 Hertz for these progenitors. This is very consistent with the actual time modulation scale of the standing shock waves. So this is consistent with the previous founding by Irina Tambora et al. So what about the neutrino and gravitational wave signals for the rotating supernova progenitor? So now you are looking at the 20-cell solar mass progenitor exploding with a rapid rotation. So this is the spin axis. The axis is the spin axis. So you can see that rapid rotation of the shock, and you can see that the scale is now expanding. This means that the shock is expanding almost homologously. So you can see that explosion is now taking place towards the equatorial plane. This is a spin axis, equatorial plane. And this is a power spectrum of neutrino signals at 10 kiloparsec for ice cube. So for the green line, the spectrum peaks around 80 Hertz, as I said. For the moderately rotating case, the spectrum peaks at 150 Hertz. And for the rapidly rotating case, the peak spectrum is about 300 Hertz. What is the difference? What is the difference? So what we found is that peak frequency of neutrino signal modulation become higher with strong progenitor rotation. This is simply because rapid rotation leads to rapidly rotating protoneutron star, and also the rapidly rotating neutrino sphere. All right. So I have to go very quickly because I have only 3 minutes. Yes, I have 3 minutes, right?
5 minutes.
5 minutes. Okay, thanks. If I have 5 minutes, that's okay.
3 minutes. Okay, sorry.
Okay. Anyway, so this is an excess of neutron emission rate seen from the equator. So you can see that hot region or high neutron emission region is rotating along the spin axis from left to right. So when the high neutron emission region is coming to us, we can see the increase of the signal. On the other hand, if the high neutron emission region is opposite to us, we can see the decline of the signal. This is a so-called pulsar. This is very analogous to pulsar lighthouse effect, right? Isn't it? And this is, as I mentioned, the modulation frequency of a neutron signal for a rapidly rotating case is 200 Hertz for this case. And looking at the gravitational wave signals, the peak frequency of the signals is about 100, 200, 300, 400 Hertz. So this is, you can see the frequency doubling between the neutrino and the gravitational wave signals. So peak frequency of the gravitational waves is twice of the neutrino modulation frequency. This is not so surprising because the gravitational wave emission is predominantly determined by the quadrupole emission. And a coincidence between gravitational wave and neutrino signals should give us a smoking gun signature of rapid rotation of the core due to the 2 times difference of the peak frequency. Now I'm showing you the most recent result from our team. So 3D full general relativistic magnetohydrodynamic simulation, including all updated neutrino physics. I have to skip there. So this is a simulation done by Takami Kuroda now at Albert Einstein Institute. So you can see that for the strongly magnetized and rapidly rotating core, you can see the formation of jets along the spin axis. But due to the kink type instability, you can see that strong explosion is obtained towards the south pole for this case. But, so this is a so-called renaissance of MHD studies. So this is a simulation by myself, simulation by Martin Obergaulinger in Valencia supernova group. This is a MHD jet by Pablo, and this is a jet by Princeton group. But this is first 3D MHD. This is the first MHD jet in full 3D general relativistic MHD simulation, with including multi-energy neutron transport. And also, I would like to emphasize that Valencia supernova group is also world-leading, done by Martin Obergaulinger and Miguel Angel Arroy. But analysis of gravitational wave and neutron prediction is still underway. So maybe this is a provocative slide, but I have to say that all what I have shown may be all wrong. So what does it mean? Because we have already all the results I have presented is based on 1D progenitor models, but we currently 3D progenitor modeling is now doable. So this is an example of 3D progenitor modeling done by Takashi Yoshida-san, and you can see that the geometry, because due to the nuclear burning, the shell structure is totally different from a 1D structure. And this is a pre-supernova neutrino signal prediction from oxygen shell burning. So this is hard to see, but the solid line is based on 1D simulation, and the red line is for the normal neutrino mass hierarchy case, and the blue line is inverted mass hierarchy cases. And the thing is, in the multi-D simulation, you can see the modulation of pre-supernova neutrino. This is simply because of the neutron convection in the burning shell. This kind of signal modulation could be seen by Kamran or, of course, by Hypercamion Kande. And long-term evolutions needs to be done to get to the final word on this pre-supernova neutrino. And this kind of progenitor inhomogeneities is very important to energize the underpart 3D explosion makes more energetic. So this is a summary slide. Sorry, I'm now running time. So we can do signal neutrino gravitational wave prediction based on 3D magnetohydrodynamics modeling, and the time modulation of neutrino and gravitational wave signals should provide the smoking gun signatures of the supernova engine, like the dominance between Sasso and the convection and the key of the rapid rotation of the core. And also we needed to signal multi-messenger neutrino gravitational wave signal prediction of black hole forming supernovae, as we have observed in LIGO and Virgo collaboration of binary black holes. And this is, I don't have time enough to go into detail, but there are a lot of new games we have to study, like the update of neutrino detectors and the physics of collective neutrino oscillation. I think we can see a nice talk by Masamichi Zaizen-san, and detailed weak interaction and action neutrino physics, action physics would impact the supernova physics, and the multi-D progenitor modeling is also important. All these new elements are entering into this field, and these are very important for updating our understanding of core collapse supernova physics and multi-messenger signal prediction. That's all. Sorry for the rush of slides, and thanks for your patience.
Well, thank you very much for beautiful slides and excellent talk.
Thank you very much.
Okay, there is one or two questions. I'd like to show it. I'd like to show some comments. Wonderful, complete, and very entertaining talk.
Oh.
Thanks for giving credit to the work of the Valencia group. It's a pity you cannot be here in Valencia in person beyond your future invitation. Okay.
Oh, thanks. I just say thanks.
May I have
okay, please. Sorry.
Okay.
Please.
May I have one question?
No, please.
It's you studied a very spinning cores for the supernova
Yes.
collapse. But the very beginning of the movie, there is a core, but there is no spinning.
Yes.
Is that right?
Exactly. So we are, as you mentioned, that we are thinking of two scenarios: the canonical neutrino scenario, in which rotation and magnetic field plays no role. On the other hand, for explain the rather energy explosion, like the explosion energy exceeds 10 to the 52 Elix, we need rapid rotation and magnetic fields. So there are two branches of supernova, like supernovae, or one may say hypernovae. The explosion energy exceeds 10 to the 52 Elix. So sorry, maybe I'm not so accurate to distinguish two things, but we want to collectively understand two mechanisms. So we pay attention non-rotating model and model with rapid rotation and strong magnetic field. Does it make sense?
Thank you very much. A bit more question. For the effect of the spinning of the cores, is that make some effect on the emitted neutrino flavors or something, nu E to nu E bar ratio for emission because of the some density difference or disturbance or something?
So you're asking, by adding rotation to the projector, we can see, the neutrino, there is a nu E bar and the heavy lepton neutrinos, and yes,
depending on
I understand. Depending on the rotation rate. Yes, I totally understand.
Yes, there's very much difference of the material density.
So location of neutrino sphere depends on neutrino spheres. So nu E spheres locates more distant from the center. On the other hand, the location of heavy lepton neutrino like nu mu and nu tau is located rather inside, deeper inside. The effect of rotation appears more clearly, more apparent in the outer region. So the impact of rotation on the neutrino, emergent neutrino spectra is more evident for the nu E and the nu E per signal, contrary to the, comparing to that of the nu X signals. Yes.
I see. Thank you very much.
Thank you very much for your attention.
So we run out of the time. So thank you very much, Kotake-san.
Thank you very much.
So let's move on to the next speaker. Next speaker, Cécile, Jollet.
Yes. Can you see my screen?
Yes, I can hear your voice. Title is the Reactor Experiment Review, including short baseline. Okay, please start.
Okay, so thank you very much for the invitation. So I will review on the neutrino reactor experiments. So I should just press this. So nuclear reactors have been exploited by many neutrino oscillation experiments since they are an intense and pure source of electronic anti-neutrinos. So the neutrinos come from the beta fission fragments from the fission of uranium-235, from uranium-238 and plutonium-239 and plutonium-241. And an important point is that all the fission products are neutron-rich nuclei. That means that they will decay by beta disintegration, and which lead to a pure electronic anti-neutrino flux. And this is really important for neutrino oscillation physics, since there are no impurities from the other flavors. So it is an intense source of neutrinos. On average, each fission produces 6 neutrinos, and for 1 gigawatt thermal power, we expect 10 to the 20 neutrinos per second. So the anti-neutrino spectrum depends on the concentration of the fissile isotopes, but it is time dependent. It depends on the fuel evolution, and so during a typical fuel cycle, as you can see here, the plutonium concentration will grow with time, and so the neutrinos from plutonium-239 and plutonium-241 will also grow with time. So taking into account the time evolution and the numerous branching, it is not so easy to predict the flux and the spectrum of the anti-neutrino. So there are two methods to predict the spectrum, the summation method or ab initio method. The idea is that the neutrino spectrum is computed as the sum of the contributions from all the fission products. And this requires a huge amount of nuclear data, as you can see here by this illustration. The second method is called the conversion method. It is based on the measured beta spectra of fissile isotopes at the ELL at Grenoble in the 80s. And the idea is to convert the integral beta spectrum into a neutrino spectrum. And to do this conversion, several beta branches are needed. And since we don't know all, the procedure is done using virtual branches, which implies some difficulties to include them. So this is the spectrum that we product. Now, what is the measured anti-neutrino spectrum? So of course, it depends on the detection channel. The preferred one is the inverse beta decay or IBD. You can see here, it is the antinui will we interact with a proton and they will give a positron and a neutron. And the signal signature is given by a twofold coincidence, which permit to reduce a lot the background. So the prompt signal is given by the positron ionization and annihilation, and the delayed signal will be given by the neutron capture. So it could be radiative capture on gadolinium or hydrogen, or it could be capture on lithium-6. It depends how the detector is doped. And so to reconstruct the coincidence, we look at a time correlation between the two signals and the space correlation. So the energy spectrum that we measured with a reactor is a convolution of the neutrino spectrum from the reactors and of the IBD cross-section. And the important point is that the cross-section, the IBD has a threshold at 1.8 MeV, and so we measure the spectrum after this energy. So the measured spectrum is the red one. And what is also important is that by measuring the prompt signal, we directly are connected to the antinui signal. So few words about neutrino oscillation. So the three-flavor oscillation is well established. You can see here the relation between the flavor eigenstates and the mass eigenstates using the PMNS matrix, which is constructed with 3 mixing angle and 1 complex phase, the CP phase. And here, this is the oscillation probability between flavors, where the oscillation term depends on the mass splitting, the baseline, and the neutrino energy. In the case of reactor neutrino oscillation, the anti-neutrino energy is too low to allow the appearance of the new flavor. And so we can only observe the disappearance. And so we look at the oscillation of the disappearance oscillation anti-nu-E to anti-nu-E that you can see here. The important point is that, as you can see, this probability does not rely on the CP phase and it does not rely on θ23, which allow for clean measurements of the other parameters. And generally, the baselines are short enough to neglect matter effects. So here you can see the anti-nu-E oscillation probability as a function of the distance to the reactor. You can see that there are several components which correspond to the different oscillation frequencies. At medium baseline, about 50 kilometers, the oscillation is driven by the two solar terms, θ12, delta n square 1, 2. At shorter distance, about 1-2 kilometers, you can see that the oscillation is smaller. It is driven by the θ13, delta n square 1, 3 parameters. And at very short baseline, we can test if there are sterile neutrinos. So in the following, I will do the review of the experiments and of their results, going from the very short baseline then to the short baseline, and I will finish with the medium baseline. So first, the very short baseline. So the first experiments which detected anti-neutrino were close to the reactors in order to benefit from a large flux, and experiments have been done close to two kinds of reactors, the low-enriched uranium reactors, which are the commercial reactors, and the high-enriched uranium reactors, which are the research reactor, non-commercial one. And these first experiments allow to compare the measurements with the predictions. In 2011, the reactor neutrino flux was reevaluated. It was done by Mueller and Toll and Huber. And so this is what we call the Huber-Mueller model. And after this reevaluation, this reevaluation resulted in a small increase of the predicted flux. That means that the experiments that took data observed consequently a deficit compared to this new prediction. And you can see here the results of observation divided by prediction for different experiments. And you can see that the mean value is about 0.94 and it is not 1. So in this paper from 2011, this deficit is called the reactor anti-neutrino anomaly, and it could be interpreted as an oscillation at a new scale, delta m square greater than 1 eV square, which implied the existence of an additional neutrino, which is not standard, and so this is a sterile neutrino. But this anomaly could be also interpreted as an incorrect flux determination. So following this reactor anti-neutrino anomaly, many projects at close distance to reactors have seen the light. The short distances allow to have high statistics and to perform measurements at commercial and research reactors. However, generally, there are not a dedicated laboratories, so it implies shallow overburden, so background from cosmic, neutron, and gamma, and generally due to the lack of space, a small detector size. So you can see here on this figure the different projects. Two main technologies are used, liquid scintillator and plastic scintillator, which are doped with gadolinium and lithium-6, and detectors can be homogeneous or segmented. So I have put in this table the different projects. I will not enter into the details of all of them. NEOS and DENSE took data close to low-enriched uranium reactors, and Neutrino 4, Prospect, and Stereo were close to research reactors. There are other projects which are still in R&D phase. They will look at sterile but also at non-proliferation. So here you can see some results about the sterile analysis. So I will be quite fast because it has been covered in the Stefano's talk yesterday. So you can see in gray the reactor anti-neutrino anomaly region with the best fit here. DENSE, NEOS, Prospect, and Stereo have rejected the reactor anti-neutrino anomaly with a high confidence level. Neutrino 4 claimed the observation of sterile at about 3 sigma with the best fit values, which is somewhere here, a delta m square as 7 eV square. But the best fit of Neutrino 4 has been disfavored by Prospect. So Stereo is now dismantled, and the detector of the NEOS, DENSE, Neutrino 4, and Prospect are upgraded, and so they will release new results in the near future. So now I will speak about the short baseline. So θ13 was the last unknown mixing angle, and it has been measured using the reactor neutrinos at short baseline. So the idea to measure θ13 was to put a far detector where we expect the oscillation and compare the spectrum with a near detector before the oscillation in order to cancel out the associated systematics. So 3 experiments have measured the θ13 measurement, Diab in China, Doubleshot in France, and Reno in South Korea. You can see the design of the 3 experiments with the different power from nuclear power plant and the different detector with the associated masses. As you can see, for Doubleshot, the target mass and the power is lower than for the other experiments, but it has the advantage feature of being in an almost isoflux configuration. So the 3 detectors, and you can see a cartoon here, have the same onion structure. So the inner part is a target. It is a liquid scintillator volume doped with gadolinium. And so we look and capture on gadolinium. Around the target is the gamma catcher, liquid scintillator not doped, but it can be used as a target if we want to do analysis looking at capture on hydrogen. The scintillation light is detected by photomultipliers, and there are around the detector and also on the top of the detector some veto in order to tag and to reduce the background from cosmic muon and fast neutron. So a few words about the IBD selection. As I have said, we have a twofold coincidence. So we do temporal and spatial selection to reconstruct IBD pairs. And you can see here the prompt energy as a function of the delayed energy with an excess of events corresponding to the emission released for the different radiative capture. In the case of double show, since the target was lower, the analysis has been done during capture, looking at capture on both hydrogen and gadolinium. So the IBD background can be of two origins. It can be accidental or correlated. In case of accidental background, the prompt signal is generally given by the natural radioactivity. The correlated background is due to cosmic background, so it could be fast neutron. In some cases, topping muon can be a background if the Michel electron is detected as a delayed signal. And one important background is due to cosmogenics, in particular the two isotopes, lithium-9 and helium-8, which will decay, emitting a beta plus one neutron. So here I come to the results of the 3 experiments. So the 3 experiments have measured the neutrino spectrum at both near and far detectors. This is what you can see for Diabe, Ueno, and double show. And doing the ratio between the far and the near spectrum, they have observed a deficit. You see that the ratio is not 1. And this deficit is compatible with neutrino oscillation, and it has permitted to measure θ13, as well as delta m square 3,2 for Diabe and Ueno. For double show, since there are only 2 reactors, they took data with reactor off, which has allowed an independent measurement of the background. So here is a table with we summarize the results for θ13, and the measurements have been done looking at capture on gadolinium and hydrogen, and for delta m square 3,2, the values are consistent with the ones from the accelerator experiments. So the experiments have compared their spectrum between far and near detector, but they have also compared their spectra with the prediction. And the 3 experiments have measured a deficit of the rate compared to the prediction. And this deficit is about the ratio is about 0.95. But they have observed also a shape distortion with respect to the predicted spectrum. This is what you can see here. This is the ratio between the observed spectrum and the predicted spectrum. And this distortion corresponds to an excess or a bump at about 4.6 MeV. And this is a new shape anomaly. So the experiments have made many tests to try to understand the origin of the shape. This bump is not due to a detector effect. The sterile hypothesis is not consistent with an excess at 5 MeV, and this bump is correlated with the reactor power and also with the reactor fuel. This is what Diabe showed firstly in 2017. Indeed, it measured the IBD yield per fission, as you can see here, as a function of the plutonium 239 fraction and uranium 235 fraction. You can see here the data from Diabe. So clearly it is not constant. And the slope is compared here with the Huber-Mueller model. And you can see that the slope is also a little bit different. And it is important just to say that this model has been rescaled since there is a 5% deficit. They have also presented uranium and plutonium IBD yield per fission. Here is the Diabe base point, and here the Huber-Mueller model base point. And you can see that for plutonium 239, it is consistent, while for uranium 235, Diabe says that it produced 7.8% fewer anti-neutrinos than predicted. So we know reinforced the conclusion in 2019, and it shows also that the 5 MeV excess, the fraction of the 5 MeV excess is correlated with the concentration of uranium-235. And Diabe shows also that there is a 7% excess of events observed for the uranium-235 compared to Huber-Mueller normalized model and a 9% excess for plutonium-239. So I will just come back to this very short baseline because they have also measured the neutrino spectrum. In particular, stereo and prospect were close to high-enriched uranium reactors. And so they're able to nail down the correlation between the excess and uranium-235. So you can see the results of stereo and prospect. They made a joint analysis and they show a preference for a bump with 2.4 sigma significance comparing to the Huber-Mueller model. Prospect disfavored that the excess that we have at commercial reactors comes from only 235 uranium. And they made a joint analysis with Diabe to reduce the degeneracy between plutonium-239 and uranium-235. So that means that the model and as well as the tiled neutrinos are put into question. So one last word about this short baseline. So Diabe, Ueno, and Doubleshaw made also parallel analysis to search for sterile neutrinos at lower value of delta n squared 4.1. Here you can see the oscillation probability at this baseline with the θ13 terms and this θ14 delta n squared 4.1 terms. And these experiments are sensitive in this mass range, so lower than 0.3 V squared, and the three experiments show no evidence of a light sterile neutrino. So now I come to the medium baseline. I will just say one word about Camland, which observed neutrino oscillation with reactors for the first time in 2002. So Camland was breakthrough since it has observed this neutrino oscillation and it has opened the way to do the measurement of θ13 with nuclear reactors. So Camland detected Anti-Neutrino from more than 50 reactors at an average baseline of about 180 kilometers with a 1 kiloton liquid scintillator detector. And the measurement allowed the determination of the large mixing angle MSW solution of the solar neutrino problem, as well as the high precision of the solar mass splitting.
Sorry, 5 minutes.
Okay. So as I have said at the beginning, with nuclear reactors, we can perform clean measurements since it is independent of the CP phase. And so reactor anti-neutrino experiment will allow to determine also the mass hierarchy. So you can see here the anti-Neutrino oscillation probability we've written with the sign plus or minus, which depends on the two hierarchy hypotheses, normal and inverted. So to measure mass hierarchy, there are several conditions on baseline and on the energy resolution. So a perfect baseline is 53 kilometers from the reactor. At this distance, the oscillation is dominated by the terms delta n squared 1, 2, θ1, 2. But if the energy resolution is high enough, it is possible to see the oscillation dominated by the delta n squared 2, 3 and θ1, 3 terms. This is what you can see here. You can see in blue the normal hierarchy and in red the inverted hierarchy. This is from Juno collaboration. And with high energy resolution, we can discriminate between the two hierarchies. So this is one of the goals of the Juno experiment, which will detect anti-neutrinos from two nuclear power plants, and it will be located at 53 kilometers from these reactors. The experiments will consist of a very large target made of 20 kiloton liquid scintillator detector. This detector will be not doped with gadolinium, and so they will look and capture on hydrogen, and the scintillation light will be detected by a large number of photomultipliers. So the coverage is really important since 1,200 photoelectrons need to be collected at 1 MeV to ensure an energy resolution of 3%. So Juno should start data taking in 2023. It will perform a relative measurement on the mass hierarchy with a sensitivity of about 3 sigma, and if they account for constraints from long baseline experiments, the sensitivity will be more than 4 sigma. Moreover, Juno, since it has a very large target mass, will be also sensitive to solar parameters, and it will perform a subversion precision measurement on several parameters. So, however, an important asset for all the spectral analysis is the knowledge of the predicted spectrum. In particular, if there are unknown fin structure, it could deteriorate the sensitivity. And that's why the collaboration will install the TAU detector. TAU will be a ton-level high energy resolution liquid scintillator detector close to a reactor at 30 meters, and the goal is to precisely measure the reactor anti-neutrino spectrum. It will also provide a model-independent reference spectrum for Juno, as well as a benchmark for investigation of the nuclear database. And since it will be close to the reactor, it will permit also to search for sterile neutrino. So I have one slide about the no oscillation physics. So as I have said, the inverse beta decay is the preferred process to detect anti-neutrinos, since it has the higher cross-section and it allows for 2 correlated signal detection, which permit to reduce a lot the background. However, anti-neutrinos from reactor can be detected using elastic scattering. That was it was the process used to set limit on the neutrino magnetic moment, for example, for the GEMA experiments or the Mu experiment. And in that case, for these experiments, they were looking for an excess of recoil electron events at low energy. And so for this research, the conditions on the background was really high. So recently, coherent elastic neutrino nucleus scattering has been observed in the coherent accelerator experiment, and many new experiments aim at detecting 7 signals using reactor anti-neutrinos. So I will not review on these experiments. It has been done by Clara yesterday, but I will just point out an important point again, is that the 7th detection channel has a very high cross-section, higher than IBD, and it does not have an 1.8 MeV IBD threshold. That means that with this channel, it will be possible to measure the anti-neutrino spectrum at lower energy, which has not been done yet. Okay, so I come now to my conclusion. So nuclear reactor provide us one of the most fruitful environments for studying neutrino. Studying neutrino oscillation using anti-neutrino reactor allows to have a clean measurements of the oscillation parameters, mixing angles, mass splitting, mass hierarchy. In particular, thanks to reactor anti-neutrino, the large mixing angle solution of solar oscillation has been determined, and the non-null value of θ13 has been measured, which has opened the way to the CP evaluation search in the left-hand sector. Comparing the measured spectra with the predicted one, some anomalies have been observed. There is the reactor anti-neutrino anomaly at very short baseline, and there is this bump at 6 MeV in the spectrum when we compare it with the prediction. So dedicated very short baseline measurements are resolving these anomalies. So what is important is to very well understand the reactor anti-neutrino fluxes and spectra. And for that, we can beneficiate from the high statistics from the measurements close to the high enriched uranium reactors, and also we can beneficiate from the measurements at low enriched uranium reactors, which allow to disentangle uranium-235 and plutonium-239 contributions. So in the future, new information on the neutrino parameters as well as the reactor anti-neutrino spectra will be given by Juno and Juno TAU data. And of course, you will have many details of all the experiments that I have cited during the parallel talks. Thank you very much for your attention.
Thank you very much for a nice talk. Okay. So there is one question. So I'm showing this this question. How much data does Juno need for the mass ordering sensitivity you presented? i.e., how soon after data taking starts will we know the ordering? How do you think?
Okay, so the sensitivity, so to have a 3 sigma sensitivity, we need to have 100,000 IBD events, which correspond to at least 6 years of data taking, 6-7 years of data taking.
Mm-hmm.
And
thank you. Mm-hmm. Okay. Okay. Are there any questions? By the way, I missed the questions in the previous speakers. So for the, I have to apologize. So for the people who make a question in the previous speakers, please send your question to the virtual forum in the virtual site. Again, I'm sorry. So another question. So I have one question. So neutrino spectrum, anti-neutrino reactor spectrum, there is also a well-known bump around 4 to 6 MeV. So they will be understood clearly soon. Can we hope?
well,
And what's the effect of the after clearing the after fixing the bump? How is the affection to the measurement precision of the oscillation parameters? How do you think?
Okay, so there is not impact on the precision of the parameters, since we have the comparison with the near detector, and the bump is observed in both detectors. So for the mixing parameters, there is no impact. Concerning the bump, from the results from all the experiments, we understand that there are contributions from uranium and both plutonium. And we don't have exactly, with the prediction, we don't know exactly how to reproduce it. But we hope that with TAU we will understand a lot more about all these spectral anomalies.
So bumps are probably due to the nuclear fuel composition.
Yes, it is.
It may vary.
Yes,
if so, there is some systematics. It may produce some systematics, I'm afraid.
Yes, so there is a correlation with the fraction of the different fissile isotopes. So of course there is a time evolution with that.
Okay, there is. Well, there is a comment for the discrepancy to reduce to 2%. Okay. So time is up, so we have to move on to the next speaker. Thank you very much. So next speaker is Ezio Previtali. Title is a review on underground laboratories. Please start.
Great. So, good morning to everybody, and thank you very much to the organizer to give me the opportunity to present this review on the underground laboratory. I would like also to thank my colleague that give me a lot of materials, a lot of information that will allow me to prepare this review on the underground lab all around the world. And I apologize to have no time to show everything, because more time is needed in order to show all the aspect that is now involved in the underground laboratory in the world. If we make a picture of the situation of the underground lab, what we see is that actually we could identify 15 deep underground laboratory in operation or under construction around the world. They are distributed almost worldwide. We have only 2 laboratories in the southern hemisphere, but it's clear that this number is growing. There are also new projects and new ideas that could became real in the future. When we discuss underground laboratory, we are looking on 2 different, let me say, 2 different aspects. Obviously, we are going underground in order to shield our detector from the muon flux, but we could have 2 different approaches. One is the approach in which you are building the underground lab using the shielding of a mountain. Is a typical case, for example, of the Sasso laboratory that is reported here. Or you can use a different approach in which you use practically a mine. This is the scheme of the Bordeaux mine in UK. It is clear that there is some differences concerning the capability to shield the muon inside the laboratory. And obviously, if we look to this paper that was published this year, you can see that considering the integral flux of the muon, the coverage changed a little bit respect to what is the vertical intensity that we could experience respect to the overburdened depth in water equivalent. Obviously, the advantage of the mountain shielding is that normally this laboratory is realized with a tunnel access that will help very much in order to install the detector, to install all the facility inside the lab. For the contrary, in the case of mine, you have to work with shaft, and then you have to take into account some difficulty in order to move all the material from the outside to the inside of the underground lab. But the 2 aspects has to be taken into account when the activity inside the underground lab has to be considered. If we look to the research activity, we have now to look at 2 different aspects, in my opinion. First of all, we have the activity that was the activity connected with the astroparticle physics. When we started the construction of the underground lab, the idea is to study real processes, so neutrino physics, double-beta decay, dark matter searches, and so on. Was it a typical idea that started years ago? And the idea was to have this area, these underground spaces, in which we could work in order to minimize the interference, looking through very real events. Now we have a situation in which also other fields of scientific research will ask the possibility to install experiment and activity in underground lab. What we see when we describe the various labs, we see that biology, geology, and other fields that are not directly connected with physics ask to have the possibility to work underground in order to maximize some possible aspect, in order to study some specific process. What I could say is that the deep underground laboratory are becoming a real interdisciplinary and multidisciplinary research infrastructure, in the sense that what the other fields of research ask us is not only the space underground, but also the technology that was developed for the experimenting underground, and also to have support in order to maximize their experimental capability. Also, another aspect that is important, that is true for all the underground laboratory, is that the facility needed for support the experiment in the underground is an important aspect to be taken into account. Time by time, there was some request that will ask to the laboratory to have a more specific capability in material selection, material cleaning, also to check, for example, the clean environment in which it is possible to implement the detector, and also some monitoring in the underground. This is an important aspect that has to be supported by the lab, in the sense that gamma ray spectroscopy or alpha counting or ICP-MS is now implemented in many underground laboratories as a real support for the experiment. The same is true also for all the other aspects. This is something that at the beginning was not in this way. When I started to work in the underground field, practically the screening activity and the screening capability comes directly from the experiments. Now, the possibility to have a real expertise in the underground lab give us the possibility to improve, first of all, the sensitivity of our, for example, for the material screening, but also to prepare clean material and to check if the procedure of the preparation of the detector will be really in a good shape. So the realization of a clean room with a radon-free environment and so on is something that is now directly connected with the capability of the underground lab to support the experiment. I try also to make a rough estimate of the underground laboratory research community. So just to make some number, what I say is that there are 15 underground labs in the world in which we have many infrastructure and facility. I estimate that there are something 100 experiments that is running or under construction. This is not 100 is well, not all big experiment, but in general, I could consider that this number is reasonable. I don't consider only the R&D phases of various activity. I estimate also there are at least 6,000 involved researchers worldwide. This number, in my opinion, is a little bit underestimated, in the sense that in my feeling, I make an extrapolation taking into account the collaboration that I see in the various labs, but probably the real number are larger. And also we have a lot of requests in manpower for the underground lab staffs. There are a growing request in funds for operation and maintenance, and also the safety and environmental aspect became more and more important. So the underground research community is, in my opinion, now is a very large community and important community. Again, when I started this type of research, there were a few laboratories, we have very few experiments, and we have typically the collaboration was made by few peoples. Now we are looking for a very large number and a very large investment for the point of view of the research that we have to implement in the underground lab. What I believe is that it's very important now to probably to move in a more coordinated activity. It is important to increase the synergy between the different underground laboratory in order to have let me say, an optimized approach for some problem that we encounter time by time when we are trying to implement new facility, new experiment, and so on. There was in the past some ideas and some network was prepared, but not in my opinion, was not sufficient, and not so efficient in respect to what is needed now. I think that now is the time probably to understand more clearly that we need a common strategy and let me say a synergic approach in order to maximize what will be the future for our underground lab and in order to help all the lab to go ahead in the best condition, let me say. What I see is that our colleague in the accelerator laboratory, accelerator-based laboratory, have a more strict connection and work a little bit more in contact and in a synergic way. Probably we have to study now an approach in which we could share our capability, our let me say, our experience in order to go ahead in a better way. Now I'm trying to make a very rapid view of some of the lab. I am not able, I have no time to look to all this lab because the time needed is too long. I'm starting from west to east, looking to this map, starting from SURF. SURF is a mine with 4,300 meter water equivalent of coverage, with the two principal shafts that will allow to introduce the material and people in the underground site. It's a very well organized laboratory with a relatively large full-time staff. What is interesting is that looking to this plot, it's interesting to see that the request of access for activity in the underground is growing time by time. This is interesting because it's represent for a laboratory, for an important laboratory in the US, that the request for having the possibility to work in underground is growing. So there are an important interest for the community to have access to infrastructure like in the underground laboratory. At the same time, if we look to the science program of SURF, what we see is that there are the classical approach, the classical request from physics, very important experiment, as I said, the Majorana, Casper, and so on. But at the same time, we have this new request that new in the sense that it was not something that became important time by time, but we have a lot of requests that come from biology, geology, engineering, and so on. This is something that if we look to all the laboratory around the world for the underground site, it's practically the same. So there are many requests in this direction, and we have to understand for the future also in which way we want to manage these two different strategies that are not of the same level and are not of the same type. SNOLAB in Canada is a very deep mine, is a very deep laboratory, something around 6,000 meters of water equivalent. It is I try to indicate here all the activities that are large hole, for example, the cube hole in which there are experiments like DEEP, PICO, or the cryo pit that is now that is prepared for a possible future Previtali experiment. And also there is the snow cavern in which there are now the preparation is now in preparation snow plus experiment. But there are also a lot of small areas in which there are a lot of experiments. And also in this case, what we see is that there are space in which we have life science that is normally not implemented at the beginning of the experiment. In particular, there are obviously a problem of space because if we are looking to SNOLAB, but also on the other laboratory, and we have a big experiment that it became bigger and bigger, we understand, for example, that for the future of beta decay, we are looking for few tons experiment that has to be installed in the underground. And at the same time, we have an increasing request of activity for smaller experiments, but in any case that are requesting underground space, we have to understand in which way we have to manage the space in the underground. Just a few words about the SNO Plus. SNO Plus is preparing. We hope to have this detector in data taking soon. The conversion between the Cherenkov water to LAB was completed beginning this year, and we hope to have this detector in fully operation as soon as possible. Also because apart of the beta decay research is very important also as a monitoring for neutrinos supernova, neutrino, reactor, neutrino, and so on. Andes is one of the two laboratories in the South Hemisphere. It's very important, in my opinion, to have at least one or two laboratories in the Southern Hemisphere in order to have the possibility to check some possible systematics in some specific research, for example, for dark matter. Andes is under construction, is a laboratory in a tunnel in this case, a relatively huge laboratory, is 70,000 cubic meter. It's just at the border between Chile and Argentina. It is covered by something around a little bit less of 2,000 meters of rock from the mountain. So as I said, the space is relatively large, and also the measure made by the study on the possible background that comes from rocks seems to be very promising. The design of the laboratory is almost complete, and what I think is very important to have as soon as possible a new lab in the Southern Hemisphere in order to be able to check also in the two parts of the Earth the possible systematics that come from some measurement. If we go to Europe, I will start with the Canfranc laboratory. It's interesting for me to see that the budget plan of the laboratory is stable, and so this guarantees the activity of the lab for a relatively long time. And this is also important to see that the people is increasing, so the staff is increasing. That will help very much in order to implement new experiments and new activities. Looking specifically in respect to what is the activity that is now ongoing in the lab, we have also in this case CROSS, for example, that is a typical experiment for double beta decay. But we have, for example, also this facility in the underground, in the clean room, that is prepared for copper electroforming. So is a facility of the lab that will be used to prepare in the underground copper. That is an extremely useful approach to have a very pure material for low background experiment. But at the same time, also in Canfranc, there are ideas to move respect to biology or biochemistry. That is some important aspect that has to be introduced in our activity for the future study. In Canfranc, there was two highlights in 2021. One is the result of the analysis that is looking for the annual modulation for dark matter, and the implementation of the next for the double beta decay searches. Switching to Bulbi, we return. Canfranc also is a laboratory in a tunnel. Bulbi in UK is a mine, so we return to a laboratory that is located in a mine. It's interesting because they build the new laboratory, and this lab facility is a large clean room of class 1000. They have a relatively large coverage of rock, is 2,800 meters of water equivalent. Also in this case, what we see is that there is a lot of activity in research for fundamental physics, drift for dark matter, atmospheric gamma ray spectroscopy, and so on. But also here we see that there are experiments on energy storage, geomicrobiology, and so on. One of the interesting aspects is that there are requests for astrobiology and planetary exploration. Also in Gran Sasso, we have some requests in this direction. It seems to be that the people that are planning to send a rover over the moon or other planets seems to indicate that the situation in the underground could be very helpful in order to understand if this approach could be applied also outside the Earth. Another important point is that they implemented a very interesting and important germanium screening facility in a clean room in the underground that will be very helpful in also to check and to select the material for very low background experiment. They reach a very high sensitivity of the order of 50 ppts for uranium thorium. That is a very good and very sensitive measurement.
Sorry, 3
yeah.
minutes. 3 minutes.
Yeah,
Sorry.
okay. In Modan, there is Modan is a laboratory in the south part of France. It's interesting also because it's, the coverage is very high. In this case, we are again in a tunnel. It's a tunnel very close to the border between Italy and France. And it's interesting to see that they are working for implement a new type of gamma ray spectroscopy, also looking for the implementation of different approaches for the shielding. That is very interesting for the point of view of the capability to minimize to maximize the shielding of the detector in order to prepare germane detector very sensitive for the future screening of material. The main activity are dedicated to double beta decay on one side and dark matter on the other side. There are cryogenic experiment that is now in running or in preparation, and there is the implementation of the Supernova, and also the cryogenic is used for Edelweiss. Switching to Gran Sasso, Gran Sasso is a large laboratory, is covered by 2,800 meters of water equivalent. We have the connection with respect to the external part using a highway. We have 3 large experimental halls for actually something that is 22 experiments that are in data taking or under construction. The total volume of Gran Sasso is 180,000 cubic meters. The main activity are neutrino astrophysics, nuclear astrophysics, dark matter search, and neutralized double beta decay. But also in Gran Sasso, we have a lot of requests that comes from biology, geophysics, quantum mechanics, test on quantum mechanics, and so on. It's interesting for me to report that in 2019, we have something around 1,000 users in the lab, coming from 26 different countries. So the community, as I said before, became larger and larger, and the interest on these activities, in the activity on the underground lab, is very important. Status of Gran Sasso. So Gran Sasso remained active also during the pandemic period, and we take data with many experiments also during the pandemic crisis. Some experiment was also installed, and now we are returned to a full operability of the laboratory. We will have the decommissioning of the LVD and Borexina that will start soon, and the plan is to refurbish all the underground spaces and to reuse the existing infrastructure for new experiments. We have also the complete installation of Luna Megavolt and the preparation of a new underground facility for low temperature testing device. We have also a new ICP-MS facility that has to be implemented for the beginning of 2022. Just to give you an idea, Nuova Officina Sergi, NOAA, is a specifically designed clean room suitable for random-free operation, in which we have also machine dedicated for bonding, PCB production, testing capability. And the idea is to dedicate this facility to produce, for example, 20 square meters of silicon PM that is to be applied for the Site 20K. This is an important infrastructure that has to be tested for production, and in this way, the laboratory became not only a place in which we have experiment, but also became a production site in which we prepare the things for building an experiment. As I said, the Luna Megavolt is in preparation. Practically, we complete the construction of the buildings. We will place the accelerator in the building beginning of October, and we start the commissioning at the beginning of the 2022. For the cryogenic new platform, the idea is to have a cryogenic platform that is not strictly dedicated to experiments, but it's something that has to be used for test and to measurement that could be as a test for other implementation in the experiment. Practically, this became a facility of the laboratory that could be dedicated for specific activity on request. I would like to show you one thing. During the pandemic period, we have the laboratory that is not so it's active, but we have the possibility to make an approach in order to reconstruct the situation of the lab in underground. We perform a laser scanning of all the site. This is the place where we put the laser, and this is the 3D reconstruction. These are the reconstruction of the old of the laboratory. It's not a camera picture. This is a laser reconstruction of the old A. And what it is important is that what we obtain at the end is that we have now a complete reconstruction of the laboratory with a global error of few millimeter over 500 meter of the complete area. This is very important for us now because in this way we can plan very precisely the new installation, but also the commissioning, and we can take care of the real space and the occupancy of all the part inside the underground area in order to manage the possible implementation of new things. Just to conclude, the last one, I would like to mention that the JMI lab in Korea is practically have completed the first part. The idea is to have this laboratory that have is practically similar to a mine, but have also an access with the tunnel. So the idea is to have a mixed laboratory in this way. The idea is that they have completed the first phase, so the first phase is completed, and they prepare it. They will prepare the second phase that will be completed in 2022. But the real start of the laboratory will be in 2023 when all the experiment will be installed in the underground. Just for the conclusion, what I could say is that many progress in design and operation of the underground lab were implemented in the last few years. As I said, the underground laboratory became an interdisciplinary and multidisciplinary infrastructure. And this is important because we have to take into account that we will receive as underground user, underground responsible, many requests that come from the outside of the astroparticle physics. I think that the community is now interested in running new experiments in underground. And also we are able to implement a new and improved facility that will strongly support the underground experiment. I believe that a coordinated action between the various underground laboratories could help very much in reaching a more efficient approach in many aspects. And I think that the news that comes from the underground laboratory indicate a very growing interest in running new experiments underground, not only for physics, but also for other things. Okay, thank you very much. And I would like to thank my colleague, and also I remind you that the underground laboratory session is well implemented in this conference, and I say to you to go to the session that is very interesting.
Thank you very much for nice reviews. Yeah, very impressed. Are there any questions? I can't find any questions now. Okay. So we are almost running out of time. So may I have one? May I have one question?
Please go ahead.
Okay. Yeah, you said there are not only the particle physics and astroparticle physics in the underground laboratory, there are also geological, biophysics or many other scientific fields are ongoing and increasing. And also there are increased number of underground laboratories. So in this trend, how do you think about the future trends or strategy in this community?
There are two different aspects. The first one is that if we consider this new field of research, the main problem that we have in the lab is that we have no experience. Let me say that the laboratory was prepared and realized, imagine to have astroparticle physics experiment in the lab. We have no experience in biology, we have a little experience in geophysics and so on. What is important to imagine in the future is that if this type of research will become more and more important, I believe that it's necessary to make some assumption that is we need to have a new capability, we have to train people, and we have to understand a little bit better what will be the future in this direction. This is one point. The second point is that if I look to the situation in Gran Sasso, what I could see is that I receive a lot of requests for the installation, and this is not a problem only for Gran Sasso, but discussing with also my colleague, I see that also in the other lab there are a lot of requests of space, but the problem is not make the space, the problem is the manpower. It says that you need to have a strong support for the experiment. And let me say strange things. For the laboratory, a big experiment is definitely better respect to a small experiment, in the sense that a big experiment arrives with having strong support, strong manpower, and they ask specific help, but is well defined. The main problem for the lab, at least for Gran Sasso, is that if I have a few small experiments, the support that I have to prepare for them in percentage is much higher respect to what I have to prepare for a large experiment. So the main problem is that in some sense of what I'm proposing is that if we have the possibility to have a more clear interaction between laboratory and to share not only the information, but also the experience and the capability, this, in my opinion, could be extremely useful, because probably some laboratory have implemented some specific things that could be transferred to the other laboratory in order to maximize the impact. Because at the moment we have to learn on each aspect, and we have to prepare the various things in order to be able to support the experiment that will ask to stay in the lab. In the past, there was some, let me say, some strategy, but in my opinion, now we have reached so important community that we probably need to go ahead in this direction and to try again to have a more strict interaction and a synergic approach for the future. That is, that's my opinion, it's clear. But
thank you very much. Okay. So there is no questions. So it's time to close the session, I think. Okay. Any comments for organizers?
Yeah, so the local organizing committee would like to thank all the chairpersons and speakers of today. And now we will relax a little bit for the weekend, but we will resume the sessions of the TAUP conference on Monday. We will have a plenary session, and also we'll start with the discussion panel and a poster session. So maybe the weekend is a good time to see all these pre-recorded talks and explore the Gather Town environment for the poster session. So to all, have a nice weekend, and we will meet again on Monday morning. Thank you.
Thank you.